So it's my pleasure to introduce Riddhipratim Basu from ICTS Bangalore. He's going to talk about bigeodesics in random.
Thanks, Bhaktininder. Thanks, everyone. So I apologize in advance because my talk will be a little off topic from the topic of the program because first of all, there will be very little negative curvature in it. I'll be mostly working in Euclidean spaces. But what I wanted to do is to introduce a very classical model in probability which might not be very well known to this audience, in the hope that you might find it interesting to think about the same questions in negatively curved spaces for which much less is known compared to Euclidean spaces where people have been studying this for the last 50 years and still very little is known. Okay, so in this week what we have seen random processes on graphs and so like we have seen random walks on Cayley graphs. So we'll consider a different probability measure on configurations on graphs. So let me introduce the model first. It's called first passage percolation. This is one of the models we'll focus on. FPP for short. So what is the setting? So we have a graph, be simple, undirected, locally finite, connected, and also infinite. And infinite is not very important for the definition, but we'll consider that. So V is the set of vertices and E is the set of edges. So you should just keep in mind the examples of either the Euclidean lattice with the nearest neighbor edges or Cayley graphs of finitely generated groups. With a symmetric generating set. So these are, sorry? Oh, speak a little louder. Okay, sure. Okay, yeah. So yeah, stop me if you can't hear at any point. So okay, so these are the prime examples that that you should keep in mind. So V is a set of vertices, set of edges. So what we'll consider is a probability measure on configurations on the set of edges. So each edge will have an associated positive random weight. So you should think of it as weight. So this is not really necessary, but makes things much simpler. So we'll consider product measure with the same margin. So for example, if you are working on the Euclidean lattice, much can be done just assuming that this measure is ergodic under translations, but we'll just restrict to the simplest possible case. So what does it mean? It means that we have a collection of independent and identically distributed non-negative random variables. Okay, so what we want to do with these weights? So we should think of these weights as lengths of the edges. So we are associating a random length with each of the edges. So if these x's were identically equal to 1, this lengths will define the usual graph metric on the graph G. So we'll consider the perturbed version of the graph metric given by these random weights. So let me define formally. Define the length of the path just by sum of the weights. For u, v, and g, define what is called the first passage time between u and v. We'll look at all paths that connect. So we have assumed the graph is connected. So just look at all paths that connect u to v, and then look at the length of that path and minimize over all such paths. Okay, it's not. So it's very easy to see that, for example, if xe is bounded below, bounded away from 0, then this infimum will be attained, and it is actually attained under much weaker conditions than that. I'll not go into the details of it. But first observe that this is very clearly a pseudometric. And if we assume in particular that the measure does not put any mass on 0, then it actually becomes a metric. So we'll actually work with that case just for just so that things become simpler. So usually, as long as one does not have too much of a mass at 0, much of the theory goes through, but it's just simpler to think of the random variables being positive. Okay, so we have defined a random perturbation of the usual graph distance metric on G. So what are the questions that we want to know, want to answer about this metric? DUV is just the usual graph metric. So we want to know if the vertices are far away in the actual graph metric, how does the randomly perturbed metric grow? Now what is the first order behavior, what are the fluctuations, and we also want to know the growth of balls, which is a related question. So this is one class of question. Another class of question which is related but slightly different is about geodesics. It's not hard to show under very mild conditions on the measure that infimum is actually attained, and if you put a further condition that the random variables xe are continuous, then this becomes a uniquely geodesic metric space. Okay, so you will also assume that for the rest of the talk. Yeah. Yeah, because there are finitely, when you 2 points, there are finitely many. Okay, so if you put some sufficiently nice moment conditions, then you can show that for any 2 points u and v, if a path goes too far from u and v, if it exits some very large ball around u and v, then it will not be competitive. There will be some path that lies within the ball, which is smaller with very high probability than that. So you can restrict to a finite set, and you know within a finite set if it's continuous, then the minima is unique, almost surely. Yes. Yeah. Right. So this is exactly that. So you should think of the weights as the length of the edges. So instead of 1, usual graph metric gives length 1 to each of the edges. So now we are perturbing it and giving it a random length. Yes. Oh, continuous random variable meaning, right, so it means that there is no atom in the distribution. So each marginal, so we have a product measure with the same marginal. So each of the weights have a probability distribution supported on 0 infinity. Continuous means that it does not have an atom. There is no point which has positive mass, yes. Okay, so these are some of the basic questions. So let me now, and these questions are very related. This is one of the things I'd like to explain in the course of this talk, that how having information about one of these quantities or one of these objects lets you infer some things about the other object. Yes. Or D is just the graph distance. Has length 1. Okay, so let me now specialize to ZT. I'll come back to a case of more general graphs later, but let me now specialize to ZD because that's where this model really was introduced, and most of the studies have been restricted on ZT. So let me say what is known about ZD or the very known about ZD. So answers to question 1. So it is called the shape theorem. Due to many people, Richardson, Cox-Tourette, Juliet, 70s, 80s. So we have seen Kingman's subadditive ergodic theorem in lectures this week. So one of the primary motivations of developing Kingman's theory was to understand this model and some related models. So let's see what is known. So let B2 so 0 is just the origin. So if you just look at, so maybe it's a good thing to give some motivation. So why people would look at this thing. So this model came originally from statistical physics, where they're looking at fluid flow through porous media. So the idea is that you start with a source of water at the origin, and then the length of the edge is the time that takes for the water to traverse that edge. So this exactly gives you the set of vertices that are wet at time t. So maybe I put a star here. I'll tell you what the star is, and then what is known is that with some mild, I'll not specify moment conditions on fixing Okay, so I should explain now what that star means. This Bt over T is a discrete set. So B is a set in R2. So in particular for this inclusion, we can't really work with B. So what this, we can't really work with this set. So the actual definition will be that this will take this set and will fatten the vertices a bit, so that it will become a nice continuous set. Yes, obviously, yes. Yes, RD, obviously. Yes, RD. Okay, so what it means is that almost surely the growth is linear. So in each direction there is a certain speed of growth, and the speed of, as you vary the directions, the speed of growth varies sufficiently nicely. Okay, so much more, something more is true. So what is true is that if you take 1 over n zd, 1 over n t, this matrix converges to, say, the base point origin, converges in the pointed Gromov-Hausdorff sense to some deterministic metric mu on Rd, almost surely. Okay, and so this set B is really the unit ball of the metric mu. And this is a very important object, it's called the limit shape. Okay, so that addresses question 1 for the first order behavior. So we have an error parameter epsilon. So if you fix epsilon, then that set will be contained within 1 minus epsilon fattening, 1 minus epsilon thinning of B and 1 plus epsilon fattening of B for all t sufficiently large. Sorry? Mu is a metric. Mu is a metric on Rd, which is the limit of 1 over nt. Yeah. Okay, so then of course one can ask finer questions. So for the shape theorem tells you that TUV grows linearly in the graph distance mu and fluctuations. So fluctuations, and this is has turned out to be a much harder question. By a standard Poincare inequality argument, so this is Kesten in '93. He showed that the variance grows linearly, at most linearly in the norm of the vector, which means that the fluctuations are at most square root of the distance. And this was a logarithmic correction, but not a correction in the exponent by Benjamin, Nicolai, and Schramm, 2003. And this argument used hypercontractivity, essentially Talleyrand's inequality, Talleyrand's general concentration via isoperimetry techniques. Yeah, so this is what the star is. So Bt is not quite this. I have fattened this. So Bt set plus minus half power d. I didn't want to I write that down. So Bt is a subset of only integer coordinates, but this set is a subset of only integer coordinates, but what my definition of Bt is, I'm fattening it. So each point, I'm fattening it by a unit hypercube. So once you do that, then the problem goes away. That's what the star is about. Anyway, so I forgot to mention that proof of this theorem is essentially applying King-Venn subadditive ergodic theorem that we had already seen before this week. All right, so, and essentially that's where we are. That things are stuck. What is believed is that there is an exponent which is strictly less than half. So if you look at standard deviation of T0V, it is believed to there is believed to be some exponent, and that exponent is strictly less than half. So for d equal to 2, physicists have very precise predictions. And it is believed that the variance grows as a power 2/3 of the norm of the vector. In higher dimensions, things become more murky. Even physicists have conflicting predictions, but the general belief seems to be as you increase the dimension, this exponent should decrease. And it seems like the prevalent belief is that this exponent should decrease to 0 as d goes to infinity. But whether or not that becomes 0 at any finite d is not very well understood. At least that's my understanding. So this is all for the upper bound. For the lower bound, the best thing we know is that there's a lower bound of log n in dimension 2 and a lower bound of a constant in all higher dimensions. So as you can see, it's wide open. There's a huge gap. Okay, so, and at this scale, so if you look at this variance of V or V over log V, you can prove concentration inequalities at the square root of that scale using Talleyrand inequality essentially. So you can show that T of 0V minus the mean minus mu of V times divided by square root of the norm of V, that has nice exponential tails. That is just by Talleyrand's inequality. And it's important, it will be important later to know about the concentration inequality, so I just wanted to mention. Okay, so, yes. Yes. B is a function, just a function of, V is a function of D and the measure. So we originally put some measure on the set of edges. So B depends on D and that measure. No, D here is just the dimension. So the shape theorem I'm talking about just for ZD. It depends on the distribution of the weights. So it depends on the measure that we put on the configuration on the edges and the dimension also. Okay, so that's pretty much the state of the art for question 1. And what turns out to be the case is that for question 2, even less is known. I mean, that sort of is related to the state of the affairs in question 1. So, so for geodesics, most of the results are conditional on some properties of that limit shape. V is uniformly curved. So all general shape theorem tells you is that the shape is convex. It doesn't even tell you that it's strictly convex. So if it is uniformly curved, or there are, I mean, you can show a little bit under just strict convexity also. Then, so this is 0, this is V, and this is the geodesic between 0 and V. So there is a thing that is defined in the literature in a vague way, which is called the wandering exponent. So this is, say this is n, this is n over xi. So xi is sort of the smallest number such that a geodesic between 0 to n, say that point is n comma n, something like that, will be contained in a rectangle of width n to the xi around the straight line joining the 2 points. This is sort of a vague definition of what is called the wandering exponent. Sorry? Yes? It is supposed to not depend on the direction v, but we don't know. So it is believed that it does not depend on the direction v. Okay, so if v is uniformly curved, it is known that is less than or equal to 3/4. So for example, it is known that the geodesics are actually, if you scale things in a hydrodynamic sense, then geodesics are actually the Euclidean geodesics. So geodesics actually follow rather closely the straight line joining the 2 endpoints, with a fluctuation of at most n to the 3/4 for a geodesic of length n. Okay, so that is one thing, and this. So let me say. But what is believed to be true, the prediction is that this exponent is related to the fluctuation exponent by the following relation. So remember, the fluctuation exponent is the exponent for the square root of the variance. And it is believed, and it's not very hard to give a heuristic, which I will not do, that this is related with the wandering exponent by the relation gamma is equal to 2 xi minus 1. So for example, for dimension d equal to 2, if you believe that gamma is 1/3, then the xi should be 2/3, whereas the upper bound is 3/4. So it's quite off. But really, that upper bound of 3/4 comes from the fact that we have an upper bound half of gamma. So if you plug that in that relation gamma equal to half, you will get xi equal to 3/4. So really, the reason we do not have a good bound on xi is because we do not have a good bound on gamma. It's proved under the assumption that the limit shape is uniformly curved. If you do not know anything about the limit shape, then nothing is known essentially. Anyway, so one thing I want to point out, which will be useful later, is that so gamma is non-negative, which means that xi, if you believe this relation, which is called the KPZ relation in the physics literature, then xi should be bigger than or equal to half. It'll be important at some point later, so just keep that in mind. So I should mention that this scaling relation is proved under some very strong hypothesis by Saurabh Chatterjee a few years ago. But under some very strong hypothesis, much stronger than just the limit shape being uniformly curved. Anyway, so these are about finite geodesics. But our interest, at least for the purpose of this talk, really lies in infinite geodesics. So what are infinite geodesics? So I take an infinite path, I take any 2 points on that. And I call that infinite path a geodesic if the restriction of the path between any 2 points gives the geodesic, we have assumed that the distributions are continuous and everything, so there is a unique geodesic between every 2 points. So if the restriction of my path gives the geodesic between the 2 endpoints for every pair of endpoints on that path, then I call it an infinite geodesic. So obviously there are 2 kinds depending on what sort of infinity you have. If you have one-sided infinity, then it's called a geodesic ray. Semi-infinite geodesic. Or geodesic line. Now let's come back to the deterministic situation, the graph metric. Obviously, semi-infinite geodesics and bi-infinite geodesics all exist. If you just take the horizontal x-axis or the vertical y-axis, these are bi-infinite geodesics. So, but once you have put random weights on the paths, it no longer is clear even if they even exist. Well, okay, so for semi-infinite geodesics, it's not very hard to show that they exist just by a compactness argument, because you take the geodesic from 0 to n, that exists, and then by a compactness argument you should be able to find a convergent subsequence of those paths, and that convergent subsequence will be an infinite path, which it's not hard to see that it must be a geodesic ray. So they exist by a compactness argument. Now, it's easy to see that if you try to construct a bigeodesic by the same argument, then you fail. You can, starting from any point, you can construct an infinite geodesic in going forward, another infinite geodesic going backward, but there is no guarantee that the concatenation of those 2 paths will be a bi-infinite geodesic, because so this is one semi-infinite geodesic, this is another semi-infinite geodesic. There is no guarantee that this path here, this point here and this point here, the geodesic between these 2 could be something like this. It is not precluded by the definition of semi-infinite geodesic. So So question of existence of bigeodesics is a harder question than semi-infinite geodesics. Okay, so let me tell you a little bit of what is known about semi-infinite geodesic and what one can from those about bi-infinite geodesics. So these are works of Newman mostly from the 90s. Newman plus co-authors. So every geodesic ray has, yes? Sorry? Yes. Yes. So it is only in law. That is not for a quenched thing. So you do not have it on the same assigned set of weights. So that this is not true for a same assigned set of weights is the next theorem. So in So in any given direction, there is a unique geodesic ray. So what will happen? See, it's actually not very hard to see because, I mean, the geodesic ray sort of picks the most favorable region for it to go through. So as long as you are going in the same direction, it does not matter however far you start from, you'll eventually be attracted to the same set of points. So picture is the following. So for a given direction, you start from one point, you get one geodesic ray. You start from another point, you get another geodesic ray, but eventually they will coalesce. So this is very different from the deterministic setting because you have geodesics not coalescing at all, but because we have introduced randomness, there is some part of the space which is better for the path to go through than others. And all the paths in a given direction will eventually find the same paths to, same points to go through. So this is under uniform curvature of limit shape. So if you have any path, you have xn, say the path, the set of vertices on the path is xn. You look at xn divided by norm of xn. So first of all, because xn divided by norm of xn lives in a compact space, there are subsequential limits. But part 1 of that theorem says that it actually has, if you take a geodesic ray, it will actually have a limit. So that is the direction. Okay, so so this actually is known only for d equal to 2. So it's believed to be true in any general direction, but as you can see, sense of direction gets more complicated as dimension increases. So it's actually known only for d equal to 2, but it's believed to be true in for any general directions. Okay, so this is this is very important for us. This is called the coalescence of geodesics. This is a very important concept, that the geodesics eventually coalesce. That's right. So that's about what I want to say for infinite geodesics. So let me come to the topic of the talk, bigeodesics. So the basic questions, yes? Yes, yes. So this is all uniform curvature. So actually for this result, also assume so something can be said under uniform curvature. Essentially, if you just assume uniform curvature, the same statement is true, but not in all directions, but at an almost sure, there might be a measure zero set of directions in which it is not true. But if you assume that the limit shape is also differentiable, then it is true for all directions. Okay. So this question goes back to Furstenberg. As attributed by Kesten. So that's so one quick observation is that the existence of bigeodesic is a translation invariant event. So by ergodicity of the underlying measure, this is a 0-1 event. So either bigeodesics exist with probability 1 or bigeodesics do not exist almost surely. Okay, so this observation is a 0-1 event. I mean, it's a sufficiently natural question, but why did Furstenberg ask this question? Sorry. So, at least the way it is written in the literature, it seems like he was interested in ground states of Ising models. So, at least in 2 dimension, it's not very hard to see, although I don't have time to show you that existence of bigeodesics imply, so you have Ising model, I suppose everyone is familiar with Ising model. So you have Ising model with random coupling constants. So, so the usual Ising model Hamiltonian is, but Ising model with random coupling constant, you also have a random variable jxy. Okay, so it's an open question in physics. Given a set of coupling constants, does there exist? So what does a ground state mean? A ground state means the minimum or maximum, depending on what sign you are putting there, of the Hamiltonian. So obviously, all plus configuration and all minus configurations, they are ground states. And the question that is still open in the physics literature is whether or not for a given set of random coupling constant, whether or not almost surely there exist any other non-constant ground states. So what is not very hard to show is that existence of bigeodesics imply an existence of a non-constant ground state of an Ising ferromagnet with random exchange constants. So these constants will just be the weights you put on the edges in the dual lattice. So there's some correspondence which I don't want to go into. So that's one motivation. So physics people believe, although it's not proved, that at least in 2 dimensions there does not exist any other ground state. So coming from that heuristic, you might consider the answer of this question to be negative. So generally believed, sorry? Yeah, so I'm not sure. So I know how to go from existence of bigeodesic to an existence of another non-constant ground state, but the way it's written, it might even be equivalent, but I'm not sure. it's not immediate to see from. Yeah, because so if there is a non-constant ground state, the boundary between the plus and minus cannot be any finite set. Right? Boundary between the plus cluster and minus cluster cannot be any finite set. So it might be possible to construct a bigeodesic out of it, but I'm not 100% sure. But anyway, so generally believed to be at least for low dimension. On the other hand, if you are coming from geometry, existence of bigeodesic again is a natural question. So I think it's a classical result that, let me look up what exactly are the conditions. Yeah, so it's a classical result that complete simply connected non-positively curved Riemannian manifolds do admit bigeodesics. So the Euclidean case, after you have put randomness, the randomness can introduce some positively curved parts in the space, right? So ZD or RD, they do contain bigeodesics, but once you have put randomness, then you might have introduced some positively curved parts in the space. So it's not immediately clear. In some sense, you can think that this is sort of a critical because the underlying graph is zero curvature, it's flat. You can think of this being the boundary between existence of bigeodesics versus non-existence of bigeodesics. So that's another reason this question is somewhat interesting. Okay, so as I said, not much is known. So let me very briefly say what is known. So there is a set of results again. So starting from Newman in 90s, and more recently, so this is 95. So all these papers prove basically the same thing under different, more general conditions. What they show is that bigeodesics do not exist. Fixed direction. So what they show is that if you fix some forward direction θ1 and some backward directions θ2, then almost surely there does not exist that is going forward direction θ and backward direction θ2. This is no, these are all in d equal to 2. Planarity is important. Yeah, thanks. Lysia-Newman might be in high dimensions, but the later ones, planarity and the Boozman function. So these are, at least the later works use Boozman function and how the Boozman function fluctuates when you look at it with respect to some semi-infinite geodesic, that kind of technology. But anyway, but they do not rule out existence of bigeodesics in some random direction. There are uncountably many directions. So just showing that in any fixed direction there does not exist a bigeodesic does not tell you anything about existence of bigeodesics as a whole. There are, so the only result that exists showing non-existence of bigeodesics in general is if you restrict to the upper half plane. So there is a result by Van Weir, I forget when, sometime in the 90s. But somehow if you are restricting to the upper half plane, you are sort of circumventing the direction problem, because you can show if you just look at the geodesics from minus n0 to n0, you cannot go below. So you can show that those geodesics have a subsequential limit which must be a bigeodesic if bigeodesics existed, and then you can do. And so another observation that goes in there is if bigeodesics exist, then there must be infinitely many bigeodesics. It's a type of Burton-Keene argument if you're familiar with those. It hinges on the amenability of the Euclidean lattice. Okay, so this is basically the state of the art for general first passage percolation. So let me now give you a heuristic that is also due to Chuck-Newman, which is rather convincing that bigeodesics should not exist. Possibly in all dimensions, definitely in low enough dimension. So suppose bigeodesics existed. Okay, so another observation is that it is equivalent, again by ergodicity, to so bigeodesics exists. A bigeodesic exists if and only if there is a bigeodesic through origin with positive probability, just by translation invariance. There are only countable points. So if a bigeodesic existed, it has to pass through some point, and the probability of it passing through any given point is equal. So we want to give a heuristic why bigeodesics through origin do not exist. So suppose they existed, what would have to happen? So take a large ball of size n. The bigeodesic must enter and exit the ball because it has to hit the origin, right? So it must enter here somewhere and exit here somewhere. So one way to rule out bigeodesics would be to show that if you take a large enough ball, probability that there exists any point u and v on the boundary at all, such that the finite geodesic between u and v passes through the origin, that is small. Okay, so that's the basic heuristic. So let's try to do some basic calculation, know what it should give. So if you believed what I said about wandering exponent, that there is an exponent such that the geodesic between u and v passes between within, so if you look at the midpoint line, there is a region of n to the psi on which it crosses with very high probability. That is what the wandering exponent conjecture that I said, right? So that would mean, again, this is a leap of faith, this is the heuristic, right? I'm not proving anything. It's a leap of faith that on that interval of length n to the psi, probability of the geodesic hitting any particular point should be roughly equal. So probability of the geodesic between u and v actually hitting the exact point origin should be of the order n to the minus psi. But only if the straight line joining u and v is actually within n to the psi distance of the origin. Right? Okay. So but the problem is that, see, there are pairs of such points, right? So there are n to the 2 times d minus 1 pairs of such points. So if you multiply that by n to the minus psi, it will be very large. So just summing over all pairs of points is not good enough. So this is where this idea of coalescence becomes important. What you believe actually is that not only that the geodesics pass through the origin through a particular point has this distribution, but you also believe that if you look at an n to the xi here, n to the xi interval here, then if you took a geodesic here and a geodesic here, they'll coalesce sufficiently quickly. So when they come close to the origin, there is actually not two different paths, it's the same path. Yes. So what you need to know is that if you start 2 points at n to the xi distance with sufficiently large probability, they have coalesced before they have gone distance n. That is what you essentially need, and that is what you believe. So if you believe this, then let's do the calculation. So instead of hitting the origin exactly, let us do the an averaging argument. So what we do is we look at a slightly smaller ball around the origin. So I look at an n/2 ball around the origin. So now what we want to calculate, rather than probability of a geodesic from boundary to boundary geodesic hitting the origin, we want to calculate the expected number of points in the n/2 ball that lie on such geodesics. If we can show that that is a negligible fraction of the total number of points in that ball, then again by ergodicity will be done. We'll be able to show that for any particular point, the probability as you increase the size of the ball, the probability that there is a boundary to boundary geodesic passing through that particular point goes to 0. Okay, so now that I have explained, so let us actually do the calculation. So there are n to the xi, right? So how many such pairs are there? So you have n to the d minus 1, this is the volume of the boundary. So you are dividing it into pieces of n to the xi, so you have to multiply by 1 minus xi, and we are taking pairs. So this is the total number of pairs of such blocks. No, one block here, another block here. And for each block, I am saying that there is 1 or 2 or 5 constant many geodesics that are actually crossing into this ball of radius n/2. So if I want to calculate the expected number of points on such a geodesic inside this ball, I have to multiply by another n, because each such geodesic, it is crossing a ball of radius n, so the number of vertices it intersects within that ball should be of order n. It should not be winding because it is trying to minimize the length, so it will not wind. And the calculation is the following. So under this condition, if you believe all my leaps of faith, under this condition, one should get that geodesics do not exist. If you do the algebra, it comes to the following. So now remember, we had this KPZ relation of xi is equal to gamma equal to 2 xi minus 1, where gamma bigger than equal to 0 gave you xi bigger than equal to half. So xi equal to half is kind of the critical case. It might or might not be attained as dimension go to infinity, but for low dimension, this is definitely believed to be the case. Okay, so what Newman's heuristic rather convincingly gives is that as soon as your wandering exponent, so if the path is sufficiently high distance, then geodesics should not exist, just because hitting a particular point becomes harder if you are wandering a lot. Okay, so that's the heuristic that why higher wandering exponent should lead to non-existence of bigeodesic. Now immediately for those of you coming from hyperbolic geometry background, this should tell you why this should not be expected in a negatively curved setup. Because Morse lemma tells us that in a hyperbolic space, all quasi-geodesics are within a bounded distance of one another. Okay, so you should expect that for hyperbolic graphs, then all the paths are close to one another, and hitting a particular point should be rather easy. And indeed, this was shown by exactly formalizing essentially what I said by Benjamini and Teixeira. So what exactly is the statement? So if expectation of x is less than, so just first moment and positivity of the weights. G has bounded degree and one Morse geodesic. So any non-elementary Gromov hyperbolic graph will have one Morse geodesic, and so with this theorem of Benjamini and Teixeira, this is from 2017. What this says is that as soon as you have one Morse geodesic, then all quasi-geodesics are close to there, and you can do a version of this to show that actually there exists a bigeodesic. Okay, so yeah, so there are some other things that recently have been done. So Legal and Nicolas Courien have recently shown that if you look at your metric space, if your graph is on random triangulations, then bigeodesics do not exist, because essentially there are large positively curved parts which creates shortcuts so that you can avoid larger and larger balls around any given point. But yeah, but for the Euclidean case, nothing much really is known beyond what I said. So very recently, I have about 5 minutes, so I'll tell you what we have managed to do recently for a variant of the. So we have managed to rigorize Newman's heuristic for a different model. So let me maybe spend the last 5 minutes telling you about that. Sorry? It's, okay. Yeah. Anyway, so I'll things. So there is a variant of model which has been very extensively studied, at least for the last 20 years. The variant of first passage percolation, but it's much more amenable to analysis because of magical exact formula. So these are last passage percolations, at least in 2 dimensions. So it's very similar with some difference. So it can be defined in general dimension, but for 2 dimension you can do a lot more. So now instead of xe, you put the weights on the vertices. So these are IID. So you can again put any general distribution, but there are some special distribution. One of them is exponential distribution, which has density e to the minus x on density x on 0 to infinity. And now it's not really a metric, but what you define is instead of minimizing, so the weight of the path is defined as before, you just sum the weight on it. Now the weights are on the vertices, not on the edges. So obviously, if you are maximizing, then it does not make sense to take all paths because you can wind and wind and wind, and the maximum will always be infinite. So to make sense of the model, it's better to restrict to directed paths. So you have U here, V here. We are looking at the paths which look like the following. So it's essentially what you're looking at. The only paths you're allowing are the ones that are geodesics in the original graph. But you are doing it in a directed manner, so the distance is not defined, if you want to call it distance, it's called the last passage time. It's not defined for all pairs of vertices, but it's defined for pairs of vertices they're lexicographically ordered. Or not lexicographically ordered, coordinate-wise ordered. Anyway, so the models are quite similar, though there are some difference, but not enough to deter the physicists. So physicists say that these are all the same. First and last, maximum, minimum. What does it matter? It's all the same, and and they're right. All numerics and everything suggests that they're right. So in particular, so there is a shape theorem here. So the growth is linear. If you divide by the linear scaling, you get a shape. And here what happens is that you can actually show that the fluctuations are of the order n to the variance is of the order n to the 2/3, fluctuation is of the order n to the 1/3, and you can show that there are concentration inequalities. So what we recently managed to, so once it comes to the bigeodesics question, there is an obvious difference. Right? So in this model, there are bigeodesics. If you look at any vertical line or any horizontal line, those are bigeodesics because those are the only paths allowed between the vertices on those paths. But okay, so those are some trivial bigeodesics. So what we recently managed to show, so this is joint work with Chris Hoffman and Alan Sly from a few months ago. So the only bigeodesics are the vertical and horizontal lines. So the basic, so essentially we follow this roadmap. The main work goes into proving the following result. If you have a rectangle of n and n to the xi, so remember xi is now 2/3. So this is actually rigorously known because I know that the variance is of the order, the standard deviation is of the order 1/3, and Kp is scaling. There is some work one needs to do, but this is actually 2/3. So what is the main statement is that so you have a geodesic u to v, and you have a geodesic from u prime to v. So you identify the pair uv with the pair u prime v prime if the geodesics coalesce in the middle third. So these two pairs are identified where this is a separate equivalence. So it's easy to see that it's an equivalence relation. So what really goes goes into proving this theorem is showing that expected number of equivalence finite independent of n. Yeah, so once this is shown, then essentially one can do a variant of the Newman heuristic that I showed you to prove that there does not exist bigeodesics which are directed away from the axial directions, and for axial directions you need to do a little more work to show that only the vertical and horizontal lines are the only bigeodesics in those directions. Anyway, the field is wide open for general distribution, even with last passage population. For general distributions away from exponential, maybe one can do. So there are some special distributions for last passage population in 2 dimension for which you can do a lot of calculations. So maybe what we can do can be done for all those distributions. But for any general class of distribution, these properties are all believed to be universal. So they are believed to hold under very mild conditions. But we are very far away from getting anything to that effect. Anyway, so I'll stop here. Thanks.
So we have time for a couple of questions.
What is the expected universality statement? That bigeodesics. So for bigeodesics do not exist in any distribution. For 2 dimension, yeah. For any distribution that satisfied, say, continuity and second moment, say, then bigeodesics. For uniform and geometric. No, so we do it for exponential. One should be able to do it for geometric. Geometric, the situation will be a bit different because the pairs will have multiple geodesics because the discrete distribution. So one might have to do a very small perturbation of the geometric to make it. Yeah, but the coalescence kind of result one can show. Yeah, so there are a few distributions in 2 dimension where there are a lot of exact calculations one can do, but other than that, it's a. So I probably should mention that the only real ingredient where exponential is used in our work is that we need to have. So for exponential, first of all, we know that the limit shape is uniformly curved, which is what was assumed in a lot of the FPP development, and also we have a concentration inequality at the right scale. So if you look at 2 faraway points, if you subtract the mean of t between those points, and you divide by the right fluctuation, then you get concentration inequality. So that really is the key thing. So for first passage calculation, what happens is that you have a concentration inequality, but you have a concentration inequality at a wrong scale. You have a concentration inequality when you are dividing by square root n, not n to the 1/3. So that is so you have to have a concentration inequality at the right scale for our proof to work.
So if not, then let's thank Riddhi again.